So hey nerds, this is Suman and in this video I'm going to show you something very much beautiful. Yeah, I thought it was beautiful, right? So this is not my theorem. Firstly, I would like to clear that this is not my theorem. I didn't invent anything, and I'm just whether I have to say it extension or not, I also don't know. But I have found very much interesting behavior of quantum particles under the relativistic condition and kinetic energy based condition, right? So I don't know whether you have already seen this phenomena or this mathematical expression in your textbooks or whether your teacher had taught you before. So I don't know if this match with your teacher. It is entirely coincidence, and I didn't learn this concept from my textbooks. And the textbook generally doesn't provide this concept. According to chatgpt, I have asked for my several dimensions sake, mathematical error, and something very much interesting concept about that. So we all know about the Heisenberg uncertainty principle, right? So basically it says that the more accurately you try to measure the position of a particle in a confined space, the more the uncertainty in momentum your increases. So basically we from our earlier classes and in our higher school level, in class 11th and 12th, even in higher level physics classes, we have learned this formula, that is delta x into delta p greater or equal h upon 4 pi, and some students might write it as in terms of reduced Planck's constant, that is h squared upon 2. So this is the relation that the Heisenberg, the channel name is also Heisenberg, right? So this is the principle given by the Sir Werner Heisenberg. So I think he is from Germany. I'm just guessing, right? So the principle is that the more accurately you try to measure something in space, the more you try to look at the position of particle in space, the more your momentum will go on spreading like something that is very counterintuitive in our day-to-day life, right? So the quantum mechanics is actually bizarre, and if it already hard, let's make it more worse. Why not? So if they can make it worse, and we also can make it worse. So in this video I'm going to show you very much intuitive process how you can actually change the position momentum uncertainty in terms of position wavelength uncertainty. So in this particular video I had two different form of the same equation, that is under a relativistic condition and under a normal inertial lower speed condition. So in this video I'm going to show you very intuitive way, I'm just using the kinetic energy term and deriving the whole concept, right, and trying to explain everything that I uh, have to do. And in second video we will derive a general formula. So the general formula actually consists of this part also. So the general formula can be reduced to the second part when a special condition is applied to it, right? So I can also say this might be our special version and there might be our general version, right? So the Einstein gave his first paper special relativity and then he gave the general relativity, right? So basically in that terms I am just saying it. So yes, you can actually reduce the equation that I am showing you here now into using the another equation, and I'm going to show you that in correct way. So if you can see that, that is also the same thing that I have done in my textbook, sorry, in the chart paper, right? So without wasting time, let us dive into the whiteboard and let's learn the concept very properly. So I think you haven't seen something like this phenomena yet. So hey guys, so firstly I am believing that you guys know about uncertainty principle, right? So you have to know about the firstly uncertainty principle first, and secondly you have to know about the de Broglie hypothesis of wavelength and momentum equation, right? So basically we need that two equation, and we need something very much interesting. We are just using the non-relativistic condition for our case. Okay, so and if you can see that, that is the relativistic case. So I'm just using from Heisenberg from Heisenberg uncertainty principle. So the basically Heisenberg uncertainty principle states that the product of position uncertainty and the momentum uncertainty is greater or equal to h upon 4 pi. Right? This is, and I would like to convince you that you have to know that the uncertainty are always positive. It cannot be negative. That's why you have to sign greater or equal to h upon 4 pi. So h is always positive and 4 by 2 pi is constant. They are always positive. Meaning the uncertainty in position and momentum would have to be a constant quantity, or it can be greater than that constant quantity, but it cannot be negative. So in this particular expression that I am going to show you, I am not using the quantum operators or momentum operator, position operator, something like. I am just doing it in a very simple manner, just to provide you the uncertainty in wavelength relation. So, and sometimes this equation can be written by the textbook is the position uncertainty and position momentum uncertainty is h squared upon 2, where h squared would be our reduced Planck's constant, right? So basically this is the first equation that the uncertainty relation provides us. So Heisenberg, according to Heisenberg, the position and momentum uncertainty is greater or equal to h squared upon 2. So basically the more you have uncertainty, the more you are certain about the position of a particle, the more the wavelength will spreads out or vanishes about that point, right? You can actually think about it like that way. So we all know that the basic idea of, I'm using from de Broglie hypothesis. So de Broglie hypothesis is nothing but momentum is nothing but the old-fashioned, very famous Planck's constant times the wavelength associated with that particle, right? So the momentum, we can write it as h upon 2 pi into 2 pi upon lambda. So basically you have knew that the momentum can be written as in terms of reduced Planck's constant h squared, and 2 pi upon lambda is nothing but our wave number. So this 2 pi upon lambda is our constant k, that is the wave number. So this would be our first equation and this would be our second equation, right? So in terms of momentum, the momentum uncertainty, you can write the momentum in terms of h squared and k. There will be uncertainty in wave number. I guess this might be the wave number because 2 pi upon lambda is always wave number. I think it's a wave number, right? So I am very much lagging here, but the concept is true that 2 pi upon lambda can be written as the k. So k might be the wave number. So I'm using 2 in equation number 1. So if you use equation, that you will get the position uncertainty and momentum can be written as h squared upon k, and this would be greater or equal to h squared upon 2, right? So the h squared will cancel out each other and vanishes, and we will end up getting position uncertainty, and position uncertainty in wave number is greater or equal to 1 over 2, and this is very beautiful relation in quantum mechanics, right? So now I am doing something very much strange that you might not accept that. So I can write uncertainty in terms of differential form. I'm writing it as like what? I'm writing dk over d lambda times delta lambda, where delta k is our uncertainty and delta lambda is our uncertainty in wavelength. So this is our slope. So I can write delta k equals, so d upon d lambda, and what we have here, 2 pi upon lambda is nothing but the wave number, that is 2 pi upon lambda, and it is delta x. So 2 pi can be taken out from the derivatives and it is 2 pi, and we can write d upon d lambda is 1 over lambda times delta lambda. So you can actually neglect the background noise, someone is calling me. So now I take the 2 pi from the derivatives and I get of this very much interesting relation, and I can actually find the derivative. If you know the derivative of this, you will immediately know that is 2 pi upon lambda square times delta lambda. So you can write your uncertainty in wave number in terms of uncertainty in this way. I hope you are satisfied with our product. So this would be my equation number 4. So from third and fourth relation, from third and fourth relation, you can actually write position and uncertainty in momentum uncertainty. So I have already told you that this would be positive, so I am just taking the magnitude, right? So this would be 2 pi upon lambda square times delta lambda greater or equal to 1 over 2. So now I am getting my uncertainty in wavelength relation, that is delta x into delta lambda is greater or equal lambda square upon 4 pi. And this is very much interesting thing about uncertainty. So you can we started from this idea, we started from Heisenberg, and we will end up getting another form of Heisenberg uncertainty principle. But in this case, we have the uncertainty as the momentum, but in this case we have uncertainty in terms of wavelength. So the textbook doesn't provide this phenomena, rather they provide this. So this might also have to be true. And you can actually check the dimension. The position uncertainty can be measured in meter and can be measured in meter, or either you can measure both in centimeters. It depends on your choice. So this is meter square, and the wavelength square is also meter square. So dimensionally this relation actually satisfies, right? So this would be our equation number 5th. This would be my equation number 5th. So I'm just going to manipulate something very much here. So I would like to show you I'm manipulating some I'm just manipulating some quantities. Like I can write delta x into delta lambda greater or equal lambda square p square by 4 pi p square. So I have done nothing wrong. I got p square in upside and p square in downside. So delta x into delta lambda is greater or equal to. So again, if you have noticed the high de Broglie wavelength, the product of lambda and p is nothing but h. So if there is a square, you will get h square. So h square upon 4 pi p square. This would be our equation number 6. I am just using equation because you might get confused where I have put something, right? So we got in terms of momentum, the uncertainty in terms of momentum. First we got uncertainty in terms of wavelength, and in terms of we get momentum. So now we can write kinetic energy is 1/2 mv square, right? We can write kinetic energy is 1/2 mv square, and the kinetic energy can be written as kinetic energy times 1 by 2 m square v square upon m. So I got m here and m here. It also makes sense. So kinetic energy can be written as the p square upon 2m, right? Right. So if we have some particle with associated some momentum, it will have always kinetic energy. So the total energy, you know, the total energy, let us say it's a total energy as E. That's the total energy would be E, and that would be equal to m naught c square, the rest mass energy plus kinetic energy. So this would be rest mass energy plus kinetic energy term. So you can actually write E minus m naught c square as your kinetic energy term, right? This makes sense. So E minus m naught c square can be written as kinetic energy we have here p square upon 2m, right? So this would be our rest mass. This would be our rest mass. So we can write it as 2m naught E minus m naught c square is equal to p square. So I write it as equation number 7. So we have another term. So we can also replace the momentum term into the energy term. right? So I'm just using in terms of energy. Now firstly I had get the position of wavelength uncertainty in terms of wavelength, and secondly I got in terms of momentum. Now I'm going to represent in terms of energy. So what would it be? So now basically using equation 7, using equation 7 in equation number 6, equation number 6, so we get delta x into delta lambda is greater or equal to h square upon 4 pi, and the p square is 2m naught e minus into 2m naught e minus m naught c squared, right? It also makes sense, right? So what we are going to do now, so can I connect it to the relative motion of particle? So you can basically say yes. So from this relation you can also manipulate something very much interesting, that the difference in energy, if the difference in this energy goes on increasing, right? If the difference of energy is goes on increasing, you will end up getting lesser uncertainty. So you can actually cause the particle, you can actually make the energy difference very much small. This makes this term small and it causes this terms to rise. So sorry, I'll tell you something very much wrong. If this term goes on decreasing, the uncertainty goes on increasing. So if this term goes on increasing, and you will end up getting this term goes on decreasing. So in order to get the better uncertainty in position and wavelength, you must have the greater energy difference between the particle, its total energy and rest mass energy. So now I'm doing very much something like delta x into delta lambda a greater or equal to h square upon, it's actually basically 8 pi m naught. So I am writing here, whether you will understand or not, I am writing e m naught c square upon m naught c square minus m naught c square. So why I am doing this actually makes sense here. I am going to show you, right? So again I will end up getting delta x into delta lambda greater or equal to h square upon 8 pi m naught. And if you take m naught c square common from this, you will get m naught c square into 1 upon e upon m naught c square minus 1. So this make also sense. So again the delta x into delta lambda is greater or equal to 1 by 8 pi h upon m naught c squared into 1 by e upon m naught c squared minus 1, right? So if you had learned the concept of something called the Compton wavelength, these terms look very much familiar to you, like h upon m naught c is the Compton wavelength. So the position and momentum uncertainty is greater or equal to, I can write it as lambda c, this represents the Compton wavelength squared upon 8 pi e upon m naught c square minus 1, right? I think it also actually makes sense. H upon m naught c can be written in terms of Compton's energy, right? And we know that the total energy increase is gamma times m naught c square. If you had little much understanding about relativistic energy, so the relativistic energy can be written as gamma m naught c squared. So you can actually replace e upon m naught c squared as gamma. So e upon m naught c squared can be represented as here gamma minus 1. Gamma minus 1. So gamma minus 1. So the position wavelength uncertainty is greater or equal to lambda Compton square, Compton wavelength squared 8 pi gamma minus 1. So this is a very much, I think it's a beautiful relation that shows the position and uncertainty wavelength of particle in terms of gamma, or it's called the Lorentz factor. So the uncertainty in position and momentum will increase if the gamma atom decreases. If the gamma atom increases, the uncertainty goes on decreasing. And it's a fundamental fact that for a given particle, the quantum wavelength is constant because h and m naught is the rest mass energy of particle is always constant, and c is the speed of light, that is constant. So the position and wavelength uncertainty can be greater or equal to the quantum wavelength if we neglect the gamma factor. But we have to include gamma factor. It does make sense. So I think it also actually makes sense, right? So basically, the position and uncertainty will always work if gamma minus 1 is greater than 0 and gamma is greater than 1. So this relation would not break if the gamma is greater than 1. So in order to evaluate the uncertainty in position and in terms of wavelength, we have to have the condition that the gamma must have to be greater than 1, right? So this is, and the lambda c can be a scaling factor. Below this range, below this Compton wavelength, you cannot actually below the uncertainty is always greater than its Compton wavelength or equal to. So below this wavelength, you cannot actually determine the uncertainty. So this is the scaling factor. Might be, I really don't know, very much interesting, but it does make sense. It's the minimum value can be lambda c, right? So the you can actually see from here the gamma cannot be 1. The gamma have to be greater than 1. It also actually makes sense, right? So in this video I'm letting this much is our general case. Let us say it's our special case. And I had derived it using kinetic energy. I had already got PDF of my paper. So this is actually in terms of the PDF says the kinetic energy based derivation. Kinetic energy based derivation. So in this video, this much, and if you had find any mistakes, I will always appreciate that mistake. I will look upon it and provide you a better way of learning the uncertainty. So guys, you can actually replace the position momentum uncertainty in terms of various terms, in terms of wavelength factor, in terms of momentum factor, in terms of kinetic energy factor, in terms of Lorentz factor. So there is very much beautiful thing hidden in the quantum mechanics. You can actually see, you can check your result in terms of wavelength, you can check in terms of momentum, in terms of energy difference, in terms of gamma factor. So it's basically very much beautiful, and I think it's an outstanding math if it works. And it works because it's dimensionally correct, and the steps I have taken actually makes sense. So because if you didn't understand this, it's not a problem, because the quantum mechanics is built in such a structure that it always doesn't make good sense. So for that, bye bye.